Mabuhay! I am Jostin Jerico Rosal, a master's student from the Department of Data Science. And today, I'll be discussing a research review on empowering large language models with hybrid RAG for Domain-Centric Q&A in Manufacturing, a paper from the Journal of Advanced Engineering Informatics. This is the flow of the presentation: background, methodology, findings, and conclusion. Smart manufacturing is the use of digital technology and analytics to make manufacturing systems intelligent, adaptive, and efficient. It also generates massive amounts of data from machines, sensors, and technical documents, providing a wide, diverse range of multimodal data. Conventional AI and expert systems rely on fixed rules and isolated data, resulting to limited reasoning. Thus, decision-making often lacks context, semantic understanding, and explainability. Existing QA and knowledge systems also cannot fully interpret multimodal manufacturing data. Thus, we can say that manufacturing data is rich but underutilized under these circumstances. And to use AI in manufacturing, we need systems to be more intelligent and trustworthy. And to ease the understanding of data, we need systems that combine structured reasoning with language understanding. To address our concerns in smart manufacturing, here are some concepts that we want to introduce in this paper. First, we have the concept of knowledge graphs, or known as KGs. In KGs represent entities and their relationships as a network. It also provides a structured, machine-readable domain knowledge that enables semantic reasoning and traceable decisions in the field of manufacturing. We also want to introduce the concept of large language models, wherein it understands and generates natural language. It excels in language fluency and context interpretation. However, it is prone for hallucinations, and it's trained on possibly outdated data. And also, it lacks on specific domain expertise. To address the concerns of hallucinations in large language models, we can connect them to external knowledge sources. One of the popular concepts here is RAG, or known as Retrieval-Augmented Generation. It's a popular hybrid AI architecture that combines information retrieval with generative models like GPT or Llama. So the goal of utilizing RAG is to ground large language models in verified, up-to-date information. And the process usually includes retrieving relevant information or data from external sources and injecting this content into large language prompt for generation. Advantages includes reducing hallucinations and improves factual accuracy, and it enables continual updates without retraining the model. There are two existing approaches of RAG: vector-based RAG, wherein it uses embeddings to search unstructured text, and you can think of it as a cheetah, where its key strengths are it's fast and it's scalable. However, its limitation is that it may miss logical relationships. Graph-based RAG is the second type of RAG, where it uses KGs or knowledge graphs for relational reasoning. You can also think of it as an owl, which symbolizes preciseness and keenness to details. So its key strengths relies on being precise and interpretable. However, it's harder to scale and maintain. So we have here the technical similarities and also differences of the two RAG approaches earlier. So here we have the illustration of a vector-based RAG and an illustration of a KG-based RAG. So as you can see, we have two phases for both approaches, which is the query phase and indexing phase. So query phase is where the user makes the actual query to the generative model. Meanwhile, the indexing phase is where the data is ingested and stored in an external source. So for the vector-based RAG, we can see that in the indexing phase, it starts with the sourcing of the documents, document ingestion, and it introduces a process called embedding process, wherein it has text chunking, wherein this document is being split into manageable chunks, and it's being converted or being converted to embeddings on what we call as embedding creation, which eventually creates the vector representations and being stored to the vector database. So by the time a query is made, the query is being translated to embeddings, and using the embeddings, it performs a vector similarity search in the vector database, and it eventually retrieves the similar vectors that are being used for context retrieval and generating the response. For the KG-based RAG, the indexing phase also starts from sourcing the documents. However, here there is a concept of constructing the knowledge graphs where each word is being mapped to another word to establish relationship in between. From there, similar groups of words are being grouped together in order to detect a community of words, and from the community of words, they are being ranked in order to create hierarchy. Eventually, the hierarchy would have like a root level, high level, and low level before it is being stored in what we call as a community sum. So during the query phase, the user makes a query, and based on the query, it selects a specific community level in the community sum, and it's being retrieved to generate the response and have the final answer. This study begins from a practical issue in smart manufacturing. AI systems can access huge amount of data, but they can't reason about it effectively. General large language models give fluent but very vague answers, while structured systems like RAG give precise but rigid ones. So neither approach alone satisfies the industry's need for both accuracy and speed, leading to the central problem that this study addresses. It proposes a hybrid KG vector RAG model that is capable of the following: integrating a structured KG reasoning with semantic vector retrieval, applying domain constraints for logical consistency, and generating explainable context-grounded answers in order to overcome the precision scalability trade-off and provide trustworthy Q&A for smart manufacturing systems. The hybrid KG vector RAG systematically integrates structured knowledge graph metadata with unstructured vector retrieval. On the right, we can see the proposed approach and the sub-processes, mainly the domain corpus collection, knowledge graph construction, vector store construction, semantic alignment layer, hybrid KG vector retrieval, and the LLM generation. For the first step, which is domain corpus collection, it collects domain-specific documents, particularly on design for additive manufacturing. And from here, pre-processing is being made in order to make it consistent to be consumed in the next steps. The second step is knowledge graph construction, wherein it extracts the structured metadata from the documents, and it builds a Neo4j based KG representing materials, processes, and performance relationship. So you can see in figure 3 the illustration of the constructed KG for DFAM, which stands for Design for Additive Manufacturing. The next step is semantic alignment layer, wherein it injects domain constraint. So domain constraint can be of two types: hard constraints and schema constraints. So in this particular layer, it also applies a schema logic to ensure consistency between KG entities and vector embeddings. The next step is the hybrid KG vector retrieval, wherein both retrieval processes from KG and vector databases are being called for each user query, and it merges the structured and unstructured results. Lastly, we have the LLM generation, wherein it feeds the hybrid context into the large language model through LangChain, combining reasoning and language generation, and it generates domain-grounded, context-aware answers with improved precision and explainability. This section discusses the experiments being done in this particular study. In regards to the dataset used, the data is from the design for additive manufacturing. This is 3D printing for quality parts, where material composition, geometry, and complexity are being taken into consideration, thus dealing with data of different modalities. Initially, 2 DFAM textual handbooks were selected by domain experts and then expanded it into 69 documents. It was then processed by LangChain PyPDF loader to get the 12 subtopics. And on table 2, you can see the 12 topics that were identified for this research. And in terms of the methods being used to compare the results, we have vector-based RAG, graph-based RAG, the proposed solution, which is hybrid KG vector, and a slightly improved version of the proposed approach, which is the hybrid KG vector with prompt enhancement. In terms of the model use, the experiments that were conducted uses GPT-4, GPT-4 Mini, and DeepSeek version 2. So here we just have the experiment setups of the groups or methods being used in this particular experiment. So we have group 1, which is the vector-based RAG, group 2, which is the graph-based RAG, and group 3, which is the hybrid KG vector RAG, and group 4, which is the hybrid KG vector RAG plus prompt enhancement or prompt engineering. In terms of the metric use, the study enforces two kinds of metric. One is general RAG metrics, wherein we have the exact match or EM. It measures the answer if it matches the ground truth reference. CP or context precision, it is the ratio of relevant content in generated answer compared to all content retrieved. And latency or the time response that is taken from the query to the final answer. The second type of metric being enforced in this particular experiment is the use of large language models as judge. Here, the answers were evaluated on technical accuracy, adherence to domain knowledge, relevance, and clarity. So the scoring scale is from 1 to 10. So let's proceed with the findings. Starting off with the results under the generic metrics, particularly on the exact match, we can see that the performance gradually improves as the RAG strategy transitions from the vector-based to the hybrid one, which is KG vector RAG with prompt enhancement. The results of the KG vector RAG with PE reflects the importance of domain-specific prompts in guiding large language models. We can also see that GPT-4 consistently achieves the highest scores. In terms of context precision, similar to the previous results, performance gradually improves as the RAG strategy transitions from vector to the hybrid models, and GPT-4 consistently outperforms the other large language models across the groups. However, we can also see that smaller models also gain substantial performance when using the proposed RAG strategies. In terms of latency, contrary to previous results, vector-based retrieval achieved the lowest latency, while other groups progressively increased their response time. GPT-4 consistently took longer than the other large language models, given that GPT-4 is a generally bigger model than the others, and DeepSeek version 2 maintained the lowest latency, indicating efficiency in response times. Now, going forward with the domain metric, we have large language model as expert judge. Here, using the same groupings, the evaluation was conducted on 3 separate trials, and similar to the general metric findings, KG vector with PE achieved the highest results, while the vector base achieved the lowest. GPT-4 scored the highest among the separate trials, while DeepSeek version 2 recorded the lowest. In terms for computing the mean or average between the 3 trials, we can see that there is a consistent inclination of the mean across the RAG models, and diverse large language models further shown effectiveness and importance of prompt engineering incorporation to improve the performance of it. Here we have examples demonstrating different RAG scenarios under the DFAM domain. So for question 1 is using or utilizing a graph-based RAG. Question 2 is also utilizing a graph-based RAG. Meanwhile, question 3 utilizes vector-based RAG. And question 4 is our proposed study, which is the hybrid KG plus vector RAG. So the layered retrieval and reasoning process ensures that the most reliable and relevant information is being utilized. Summarizing the findings and observations through the experiment, we can say that hybrid RAG plus prompt enhancement achieves the best performance, particularly with GPT 4.0, with KG vector plus the prompt enhancement recorded the highest accuracy. Also, there is a constant improvement across models. So large language benefited more, but even the smaller ones improved notably. There is a trade-off between accuracy and latency. Here, hybrid and PE approaches increase computational load and response time, but it significantly provides enhanced precision and contextual relevance. In terms of robustness and scalability, the framework remains effective even with smaller models and limited data. Practical implication, it offers trustworthy, explainable solution for complex manufacturing queries. As a conclusion, this research introduces a hybrid approach that integrates knowledge graph reasoning with vector RAG. It also addresses the concern by bridging the precision scalability trade-off of RAG implementations and researches, and it demonstrates how structured reasoning layers improve traceability and explainability of large language model responses. In terms of limitations, there is limitations on context wherein the proposed method is tailored to smart manufacturing. Thus, initial collection and preparation of specialized knowledge might need to be adjusted for other domains. In terms of the KG construction, improving its timeliness is still a challenge for the researchers as it is being constructed manually by domain experts. Lastly, external knowledge limitation, wherein there is a challenge on keeping up with the trends and updates from outside resources. Future works and researches from limitations. First is dynamic domain adaptation. Future researches or proposed solutions will have to be more dynamic in terms of not being confined in one domain only. Next is automatic knowledge graph updates, wherein updating the graphs or creating the graphs wouldn't require intervention from human experts. And lastly, real-time and edge integration, wherein the proposed solution would be able to keep up with the latest trends and updates from external resources. With that being said, this ends my presentation on this paper. Hope you learned a lot. Thank you for listening and have a good day. Maraming salamat at magandang araw.